Next we will see what is moving ion repulsion type instrument. A soft iron piece gets magnetized and develop north and south poles when it is brought near or into the magnetic field produced by the magnet. So, the soft iron piece placed in a magnetic field gets magnetized and it develops north and south poles. When two such iron pieces of like poles brought near gets repelled. So, two such iron pieces of like poles brought near gets repelled. So, this is the basic working principle of moving ion repulsion type instrument. Soft iron piece placed in a magnetic field acts as a magnet developing north and south poles. When two such iron pieces of like poles brought near gets repelled. So, this repulsive force is responsible for the deflection in moving ion repulsion type instrument. This is the most commonly used type of instrument. So, based on the design, this moving ion repulsion type instrument is further classified into two types. Types of moving ion repulsion type instruments. So, first type is radial vane repulsion type instrument. So, based on the design, it is classified into radial vane repulsion type instrument and coaxial vane repulsion type instrument. First, we will see what is radial vane. This is the most sensitive type of instrument and it is most commonly used for AC measurement and it has a linear scale. We see the construction of radial vane moving ion repulsion type instrument. So, there is an arrangement which is used for the coil. The coil will be placed here. So, this one is the, so in the center there will be a spindle arrangement. So, through the spindle an iron piece will be connected this one is the iron piece. So, this one is the fixed iron piece or fixed vane. This one is the movable vane. Into the spindle, control spring is used to produce the controlling torque and it has a pointer connected to the same spindle. There will be a pointer connected to the same spindle and this pointer moves over a graduated scale. Okay, this one is the diagram for moving ion radial vane type repulsion type instrument. Let us see the construction for moving ion radial vane type repulsion type instrument. First one is the iron veins. So in this we have two iron veins. We have two iron veins which are radial strips of iron, made up of radial strips of iron. So among the two veins, one is fixed vein and it is attached to the coil. So we have two veins. This is one vein and another one is, this is another vein. This one is a fixed vein which is connected to the coil, which is fixed to the coil, and a second one is, so another one is movable vein which is connected to the spindle. So both these veins are placed in the magnetic field of the coil. The coil surrounds this two iron veins. Next one is field coil. So field coil is used to produce the required magnetic field when it is energized. It's used to produce the magnetic field when it is energized. Next one is control springs. This control springs usually made up of phosphor, bronze, hair springs. This is used for producing controlling torque Tc and it is connected to the spindle. So here the control springs are mostly used in portable moving iron instrument which is used for producing controlling torque. So here the one end of the spring will be connected to the spindle. So in the spring we have two ends. One end is connected to spindle and other end will be connected to a lever or arm which is actuated by a screw placed in front of the instrument. So the control springs are used for producing the controlling torque. Next one is pointer. So this pointer is connected to the spindle which moves over the graduated scale. So these are all the parts of a moving iron radial vein type repulsion type instrument. Next we will see the working of moving iron repulsion type instrument. Let's look into the diagram. The working is when an alternating current flows in the coil, when alternating current which is to be measured flows through the coil, both the iron pieces gets magnetized, that is both the iron veins gets magnetized with like polarities. That is, if the top of the iron piece achieves north pole and bottom is magnetized with south pole. So both the iron veins gets magnetized with like polarities induced on the same side of the iron pieces. When the current, alternating current flows through the coil which is to be measured flows through the coil, what happens? A magnetic field will be produced. Because of that magnetic field, this iron piece placed in that magnetic field gets magnetized with like polarities induced on the same side. Hence, due to the like polarities, there will be a force of repulsion between these two iron pieces. Since one iron piece is fixed with the coil, because of the force, repulsive force, this movable vane will move because of that repulsive force. So, that repulsive force will be directly proportional to the deflection of the pointer, because this moving iron piece is attached to the spindle where the pointer is also attached. So, because of the repulsive force, this iron piece, this moving iron piece moves through the spindle so that the pointer also deflects. So, the deflection of the pointer will be directly proportional to the movement of the movable vane. So, the movement, whatever may be the direction of current, the movement of the iron piece will be in the same direction. So, the deflection produced by this pointer theta will be directly proportional to the current flowing through the coil. So, when the current flows through this, coil, the moving iron rotates so that the pointer also rotates, where both are connected to the same spindle, which produces the deflection proportional to the current. Next one is the controlling torque. Here is produced by the phosphor bronze hair springs. So, since the phosphor bronze, one end of the phosphor bronze hair spring is also attached to the spindle, what happens is it produces a controlling force which opposes the movement of this iron vane, that is the deflection force or the repulsion force which causes the moving iron to rotate. So, this controlling force developed by the spring will oppose the movement of the iron vane, so that at equilibrium position the pointer will come to rest at a steady state position. So, otherwise the pointer will oscillate. Once the current through the coil is removed, what happens? The iron pieces gets demagnetized, so that the pointer must come back to the zero position. So, without this control springs, the pointer will never come back to that zero position. So, the necessity of the control spring is to produce the controlling torque. Next one is damping torque. So, here also air friction damping is used. I have not mentioned this diagram as seen in the attraction type instrument. Here air friction damping is used in order to damp out the oscillations of the pointer. Why we are using air friction damping is, here using a coil to produce a magnetic field. We are not using permanent magnet to produce the magnetic field. So, the magnetic field produced by this coil, which acts as an electromagnet, will be weak. So, for that purpose we are using air friction damping in case of moving iron instruments. So, because of air friction damping, the scale of the moving iron instrument will not be uniform. This is the working principle of radial vane type repulsion, moving iron repulsion type instrument. Next we will see the another type, concentric vane type. Next type is concentric vane type instrument. So, here we have two concentric vanes. Among the two concentric vanes, one is stationary and attached to the coil, and other free to rotate coaxially inside the stationary vane. Next we will see the construction of concentric vane type repulsion type instrument. Here we are having a fixed coil. The center of the fixed coil will having a spindle. Through the spindle, a moving iron piece will be attached, and the fixed iron piece will be attached to the coil. So, this one is the moving vane, and this one is the stationary or fixed vane. It's a field coil which is used to produce the magnetic field, and we have a spindle. To the spindle we have a controlling springs to produce controlling torque, and to the same spindle we have a pointer which moves over the graduated scale. This pointer will move over the graduated scale. So this one is the pointer. So only difference in construction of concentric vein type and radial vein type is here the fixed vein will be in the shape like this, which will be attached coaxially with the coil, and the moving iron piece will be connected to the spindle as it is in radial vein type. Only difference is the construction is the stationary vein in both concentric and radial vein type. So working principle is same as radial vein type. When a current passes through the coil, what happens? It produces a magnetic field. So the iron pieces, stationary iron piece and the moving iron piece gets magnetized and develops like polarities, which is induced on the same side of the iron pieces. When it develops the like polarities, what happens? The like polarities will repel each other, so that because of that repulsion force, this moving iron vein will rotate along with the spindle. When the spindle rotates, the pointer which is connected to the spindle also moves over the graduated scale. So this movement of the iron piece produces the deflection torque, and the control torque is produced by this control springs. So the deflection torque is produced by the movement of moving vein, that is moving iron piece or vein, and controlling torque is produced by the control springs. Since one end of the spring is connected to the same spindle where the pointer is connected, it will be under tension, so that it will produce a torque which opposes the deflection torque in order to make the pointer to stand at steady state position. Okay. So we can say that the controlling torque and deflection torque opposes it with each other and will make the pointer to rest at steady state position. When the current through the coil is removed, the pointer will come back to the zero position with the help of this controlling torque. Next one is damping torque. The damping torque is produced by air friction damping, as it is in case of moving iron attraction type and moving radial vein type, repulsion type. Air friction damping is used. Why air friction is? No permanent magnet is used for producing the magnetic field. So air friction damping is used because the magnetic field produced by the coil is very weak. So eddy current damping cannot be used. So we can say that generally whatever may be the direction of alternating current, it is clear that the iron pieces are so magnetized that there is always a force of attraction and repulsion in both the types of instruments. So generally we can say that moving iron instruments are polarized instruments. Why you are calling it as polarized instrument is, it is independent of direction of current. It is independent of direction of current. So it can be used for AC as well as DC measurements. So it can be used for AC and DC measurement, for it is rarely used for DC measurement but can be used for DC measurement. Next we will see the torque equation for moving iron attraction type and repulsion type instrument. Generally the general torque equation for moving iron instruments. So based on the design it may vary, but the operation of all moving iron instrument is same. So the torque equation of moving iron instrument is derived by considering the energy relations when small increment in current is supplied to the coil of the instrument. So by considering energy relations when small increment in current dI is supplied to the coil of the instrument. So, due to the small current dI, what happens? There is a, let d theta be the small deflection produced by the pointer under deflection torque Td. So, because of this, a small mechanical, due to this small increment current, a small increment, that is deflection, will be produced by the pointer under the deflection torque. So, due to which mechanical work is done. Therefore, the mechanical work done is given as the deflection torque Td and the small deflection produced due to the increment in current dI. Let us take this as first equation. So, here the moving iron vein moves in such a way so as to increase the flux of the electromagnet, because the vein tries to occupy the position of minimum reluctance. So, the force produced is in a direction so as to increase the inductance of the coil. Okay. Let us consider I as the initial current, L instrument inductance, theta as the deflection of the pointer, and dI, d theta and dL be the small increment in current, deflection and inductance of the instrument. So, in order to affect the dI in the current, in order to affect an instrument dI, that is increase in voltage, which is given by, increase in voltage is given by E is equal to d by dt of L into I. Since L and I both are changing, can write it as I into dL by dt plus L into di by dt. Both L and I are changing. So, the electrical energy supplied is given by E into I dt, which is equal to I dL by dt plus L into di by dt into I dt. So, we will get I square dL plus L into I into di. So, the electrical energy supplied is given by EI dt is equal to I square dL plus L into di. So, let us take this equation as equation number 2. So, now because of the increment in current, the stored energy increases from half Li square to half L plus dL I plus di the whole square. There will be a small increment in inductance L dL, small increment in current di. So, the stored energy increases from half Li square to half L plus dL into half into I plus di the whole square. So, the change in stored energy can be calculated as half L plus dl I plus di the whole square minus half Li square. So removing the bracket, we will get half L plus dl. So expanding this equation, I square plus di square plus 2I di minus half Li square. I have taken 1 by 2 as constant, and by removing the multiplying the both the brackets, get L I square plus L di square plus 2 IL di plus I square dl plus dl di square plus 2I di dl minus L I square. So neglecting the second order and higher order terms, so the neglecting the second order and higher order terms, get dl di square 2il dl li square minus li square gets cancelled. When I am neglecting the second order terms and higher order terms, I will get it as half two Li di plus I square dl. I will get this two terms, which is equal to Li di plus half I square dl. Let's take this equation as equation number 3. So by law of conservation of energy, the electrical energy supplied is equal to increase in stored energy plus the mechanical work done. Electrical energy supplied is equal to increase in stored energy plus mechanical work done. So from equations 1, 2 and 3, we can substitute the values. Electrical energy supplied is equal to I square dl plus Li di, and increase in stored energy is Li di plus half I square dl plus mechanical work done is Td into d theta. So Li di gets cancelled. So we will get Td into d theta is equal to half I square dl. So reflection torque Td will be equal to half I square dl by d theta. So the reflection torque Td will be in Newton meter, L will be in Henry, and theta will be in radians. We always know that all the measuring instruments are current carrying instruments. So while the controlling torque Tc is equal to K into theta, here we have used control springs to produce the controlling torque, where K is the spring constant. You can take this equation as equation number 4, and Tc equal to K theta as equation number 5. At steady state deflection, we know that the controlling torque will be equal to the deflection torque. So substituting the values of controlling torque and deflection torque, half I square dl by d theta, you can find the value of deflection theta, which is half I square by K dl by d theta. This is the equation for deflection. So from this we can say that the K is constant and d theta value varies. the theta is directly proportional to the square of current flowing through the coil. That is, the deflection produced in moving iron instrument is directly proportional to the square of current flowing through the coil. So, the current here will be the RMS value. So, current is RMS value. So, always the deflection torque TD will be unidirectional, whatever may be the direction of current. Whatever may be the direction of current, the deflection torque produced will be unidirectional, since deflection is directly proportional to square of current. Let us see the advantages of moving iron instrument used for both AC and DC measurement. So, it is independent of direction of current. Second, we will get frictional errors, because the current carrying part coil is very heavy, which is stationary, and the moving parts are light in weight. So, the torque to weight ratio will be high. So, it will cause frictional errors. Second one is cause friction errors which is very small. That is very cheaper, because a single type of moving element can used for wide range. So, depending on the range of the instrument, the coil size may vary or the number of turns of the coil vary, but the moving element will be same for all range of instruments. So, the moving iron instrument is very cheaper. It is robustness and reliable, because there are no current carrying movable parts, and it is accuracy. It has accuracy of less than 2%, and also range can be extended. Disadvantages: scale not uniform, and errors occur due to stray magnetic field. Next, we will see what are the errors in moving iron instruments. Since it can be used for both AC and DC measurement, so errors with both DC and AC is, first one is hysteresis error. So, because of hysteresis effect, flux density vary for same current. For same current value, the flux density varies. For descending current, flux density is high, so the meter reads high. So, we cannot measure the accurate reading. So, because of this hysteresis error. When the current is ascending, there is ascending current, flux density is low. So, in order to eliminate this error, we can eliminate this error by using small iron piece, so that it can demagnetize quickly when the current to the coil is removed. Second one is temperature error. This is due to effect of temperature on temperature coefficient of spring. So, this is mainly caused in voltmeters where the self heating of the coil takes place. Self heating of the coil takes place when there is a change in the resistance of the coil and also the series resistance. So, the coil temperature increases, which decreases the resistance of the coil and also the current for the given voltage. So, the reflection will also be reduced. So, for removing this, the series resistance in voltmeters is made up of a material called manganese in order to reduce the temperature coefficient. Since manganese has small temperature coefficient, that is used for removing this temperature error. Next one is stray magnetic field. Since we are not using permanent magnet to produce these magnetic field, so no permanent magnet, so the operating magnetic field produced by coil is weak. So, depending on the direction of the stray magnetic field with respect to the operating field, the readings will get affected. So, the stray magnetic field can be eliminated. How we can eliminate stray magnetic field is by shielding the instrument with iron case. With iron case, we can eliminate the stray magnetic field. Next one is frequency error. Because of change in frequency, it affects the reactance of the instrument. Reactance of the coil is affected when there is a change in frequency, because the current flowing through the coil will be directly proportional to the deflection of the pointer. So, the deflection gets affected due to change in frequency. So, the deflection for the applied voltage decreases at high frequency. So, the deflection decreases at high frequency than at low frequencies. So, in order to reduce this frequency errors, the reactance of the coil must be maintained. Eddy current error. So, there will be a small eddy currents which will be produced in the iron vanes of the instrument. So, because of that eddy current, there will be a frequency error. Frequency changes, the eddy current changes, which affects the current of the instrument. So, these are the various types of errors in moving an instrument: hysteresis error, temperature error, stray magnetic field error, frequency error and eddy current error. Now I would like to show the moving iron instrument used in laboratories, which we have seen in our class. This is the moving iron type voltmeter which is used for AC measurement. This is the outer case, the graduated scale over which the pointer is moved. So, we have seen the construction and working of moving iron instrument. So, this one is the coaxial vane type moving iron instrument. We are having a pointer which moves over the graduated scale, and we are having a coil. This one is the moving iron piece. When the moving iron moves, the pointer also moves along with this. To the spindle, there will be a control springs produced. Cosper-Bronze control springs are used to produce the controlling torque. The mirror is used for taking the readings without any parallax error. This one is concentric vane type moving instrument. This one is the coil. Inside the concentric vane pipe, we have a fixed coil. This one is the fixed coil, and we are having a moving vane. This one is the moving vane. which will be connected to this spindle which has a control spring and the pointer. This moving iron vane will be kept inside this stationary vane. So when the coil is excited, what happens? This moving vane and the stationary vane gets magnetized, and because of the repulsion force, what happens? This moving vane will move. So due to the movement of this moving vane, what happens? The pointer also moves. So this is the working of moving iron type instrument. In this class, we have seen what is moving iron type instrument, which is used for AC as well as DC measurement, and the types of moving iron instrument, moving iron attraction type and moving iron repulsion type instrument, and we have derived the torque equation for the deflection of the pointer in moving iron instrument, and also we have seen what are all the various types of errors taking place in the moving iron type instrument. Thank you.